Good day. I want to talk about Aristotle's concept of privation as cause and the nature of reality. First, my understanding of the subject of Aristotle's texts that treat privation is gleaned from an unpublished paper provided me for comment by Robert Daly, a friend of mine. Daly seems to take issue with other interpretations of Aristotle's privation and argues that the concept was a fundamental basis for Aristotle's theory of form, which includes everything that comes to be and everything that passes away. In other words, reality, what I would call reality, which Aristotle believes to be constructed out of contraries. He employs two examples, colour and musical tone, which, in the case of colour, he believes all colours are made from a mixture of different parts of the contraries, black and white. The reason I am very interested in this belief system is that roughly around 2006, I believe I had arrived at an explanation of the physical world. That is, the world we perceive, in rather similar terms. First, back to Aristotle. Daly refers to the Fechner wheel experiment, where a wheel consisting of strips of black and white in a radial sequence can appear to show colours when it's rotated. But the explanation of this is simple. It's just that the retinal detector nerve cells have different sensitivities for different primary colours, and so their individual relaxation times are different, and therefore a colour signal will be produced at certain frequencies, switching them on and off, on and off. The obvious system where two components, two contraries, Aristotle's contraries, create a reality is the digital system, where all analogue forms are built up from zeros and ones. You could say black and white. It's just a model. So music, as we now all know, can be recorded and turned into a digital sequence which is entirely made up from the contraries, 0 and 1. The same with colour. The videos we watch on YouTube, in fact the video you're watching now, they're all made up of noughts and ones. The idea I had related to my daughter's computer game, The Sims. The Sims is a basic digital world created with a program in which you generate characters and then place them in a crude digital universe with inside the computer and allow them to run around and fall in love and go to work and earn money and go to jail and all the things that people do in the real world out there, build houses and so forth. In passing, they live an extremely boring life, a Western sort of Hollywood life. And you could argue that the program is some kind of social engineering thing for children. How to live when you're a grown-up. Anyway, my idea was to ask, in a thought experiment, what would happen if I placed some scientists into this sim system. And I asked my scientists to investigate the nature of reality. Going back to Bishop Berkeley, the idea of being able to prove that reality was an illusion, is an illusion, has always been answered by philosophers and now by physicists with the conclusion that you could not, that there was no experiment you could carry out that would enable you to prove that you were inside an illusory world, a computer world. And even recently, with a lot of discussion about this area, following films like The Matrix, it's been concluded generally that such a proof is impossible. But wait, there are two phenomena that have emerged in the last 100 years that have been variously explained with unpersuasive, certainly to me, theories. These are quantum theory and its associated phenomena, entanglement and action at a distance and quantum mechanical tunneling and so forth, things that appear to be impossible. And the other thing is relativity, special relativity, starting with special relativity. and then extending to general relativity. I've been fascinated by both of these theories since I came across them at the age of about 16, and I've thought about them pretty much ever since. Well, we'll start with relativity. To me, from the beginning, and ever since, the idea of the velocity of light being constant in all reference frames seemed absurd. It is absurd. To make it work, you have to assume that length altered, really altered, with the velocity of the measuring rod that you use to measure length. Okay, relative to a stationary object in another reference frame, the argument put forward by Eddington when he was describing Einstein's theories in his famous book, The Nature of the Physical World, you can accept that because of the time it takes for the light signal to travel to you in a stationary frame of reference and all that stuff. But the problems that emerge from the Einstein interpretations, especially the necessity to curve space-time and all that gravitational nonsense in general relativity, is too much. Obviously, in general relativity, you have to curve space-time because time and space change according to your relative velocity. And so if your measuring rods are changing their size, then you've got to have curvature to make things fit. Anyway, I thought this was nonsense, and others did too. Hendrik Lorentz, the mathematical equations man who wrote down the original equations for all of this stuff, and more important, A.N. Whitehead, Alfred North Whitehead, the mathematician, also took issue with relativity, didn't believe Einstein's interpretation anyway. Whitehead had an approach that dealt with the issue on the basis of reconsidering what time was. And that is the key, as we shall see. But in this note, I won't take that one further very much. Here I want to follow my physicists in the Sims. There they are, doing their experiments. Let us ask them to measure the speed of light. In the computer now, the fastest speed for one of light that can be measured, the fastest speed that can be measured is the speed it takes for one pixel to replace the next pixel. That is the time, that is how the computer works, the time it takes for one frame to be replaced by the next frame in the bus. This time is regulated by the clock speed. On my laptop this is 2.5 gigahertz, so the speed of light measured by the Sims would be the pixel size determined by the resolution of their reality, or rather our view of their reality, divided by 2.5 times 10 to the 9, 2.5, 0.0000000. It's a very small amount of time, boom. But the speed of light in their world, in their computer world, could never exceed this. Of course, they don't know they're in a computer world. All they are is scientists trying to measure the speed of light, and they get a number, and that would be the number. The number is defined by the clock speed of the computer that they're in, but they don't know they're in a computer. The speed of light in their world can't exceed this. So a computer world Einstein might advance various theories to explain it. And the computer world Lorentz would calculate the equations that he calculated, that 1 over 1 minus square root of v minus v squared upon c squared. In his case, c would not be the speed of light that we see. It would be the speed of light that he found relating to the clock speed of his computer. Whitehead's idea to base the concept of nature on time was prescient. Reality is a sequence of time steps, time snaps, like photographs following each other at a frequency. But what frequency in the real world? We know the frequency in the computer world. What's the frequency in the real world? And here we move to quantum theory, another weird area of physics. My introduction to quantum theory was via chemistry and spectroscopy. I guess I still am a chemical spectroscopist. I've worked in the pharmaceutical industry as a spectroscopist, looking at molecular interactions and molecular structures, and I've done 3 PhD courses in different spectroscopies. Spectroscopy is a fantastic way of imaging the universe. I taught quantum theory at the University of Kent for a time, though I don't believe it. It has various equations that you can teach and various explanations that you can give. where quantum theory came in long ago was the discovery of spectral lines in the visible region for the simplest element, hydrogen, and their interpretation, the interpretation of the spectral lines. It seemed that for atoms only certain energies for electron orbits were permitted. And light was released when an electron dropped from one orbit to the next orbit of lower energy, or light was absorbed of a particular frequency equal to the difference in energy between the two orbits, or whatever orbits. So it seemed for atoms that only certain energies for electron orbits were permitted. And now with wave mechanics we use a probabilistic concept called orbitals, but nevertheless the orbits will do for the purposes of my little talk. The theory dealt very effectively with a problem that was then extant in science called the ultraviolet catastrophe problem, where electrons spiraled into the nucleus, which they would through energy loss normally. And it dealt with that because they couldn't spiral into the nucleus because they only had these fixed orbits. And they couldn't do anything else. They were sort of constrained. But this idea raised a lot of very interesting questions about these crazy manifestations that appear to be occurring. The equation that described the quantum phenomenon was the Planck equation, where you have energy equals h times frequency. H is the Planck's constant. So in other words, energy is proportional to frequency, and it's always written like that. E equals h nu. Nu is the Greek letter which is always used for frequency by physicists. H is a constant, as I said, the Planck constant, and the units are energy time, so erg seconds originally, now they're joule seconds. They refer to a frequency which is very, very high, so in other words these things are happening much more quickly than my computer, infinitely more quickly, but still not infinitely, very high, very fast. In the computer world, the astute scientist, an astute scientist, me, if I put myself into the system and walk into the group of scientists there sitting about trying to figure all this stuff out, they might rewrite this equation focusing on time. So instead of writing E equals h over h nu, you could write nu equals E upon h. Now that is interesting, because what that does is it turns the whole problem on its head, and instead of quantizing energy, you now quantize time. In other words, things can only happen at certain times in this system. They can happen now or then, or then, or then, but not in between. Understand? So in this formulation where time is quantized, it's the same as Whitehead's belief in nature, although he didn't know about computers and the digital developments at the time he was writing his philosophy in the 1920s. It's interesting that he never, later on in his life, came back to realize that he'd been describing the quantum world. Of course, he died in the 50s, so at that time the computer world hadn't really got going, and in the 50s computers were enormous great things with vacuum tubes and so on. They were a bit of an exotic area. So, to come back to the argument, what do we know in the world that employs this quantum reality, where one frame succeeds the previous one very fast? Well, of course, it's the computer, where our sim scientists are sitting in the room and discussing possible explanations. There we have a Sims Einstein and a Sims Heisenberg, and Sims Dirac, Sims Schrödinger, Sims Bohr, Max Born, all those people. Well, they later find all kinds of other ghostly phenomena, for example, ghostly connections at a distance. Of course, all these phenomena would apply to everything in the system, because everything in the system is connected by the fact that each instantaneous change in the total system is shared by all the things that exist at that time of the change, in that pixel bus space or time. Hence quantum entanglement, of course. I've thought a lot about this. It potentially explains a lot of things. It explains religion, subroutines, ghosts, subroutines, second order interactions, goddesses, things disappearing and reappearing, synchronicity, sheldrake phenomena, paranormal phenomena generally, a lot of things that ordinary people see and believe all the time. But science rationalists like Richard Dawkins, or more recently online Sabine Hossenfelder, who I like, laugh at. Think of William Blake and Newton, famous painting of the naked man sitting on a rock on the beach and measuring a little patch of light while all around him is darkness. This is science. We have to think outside this kind of rational world view and think of other things, think of other possible explanations for what we see, what we all find in our lives and in our souls, if you like. Anyway, this short videos is really about Aristotle's ideas of privation. It began as a response to my friend Robert Daly. I mean, that's all I know about Aristotle's ideas, but it's enough to know that. My main observation is that in some way Aristotle's theory of everything was pretty clever, and in some way right, as I see it. Well, what is left to ask? Well, of course, there's a number of things. The main one is who set up the system, if it exists. Though that is not really necessary. Perhaps it's just how the system works. Why not? And another question, if you're talking about who set up the system, God, for example, I mean, it's the same sort of argument, isn't it, that you pose to the Christians, you know, and to other religious people. You say, who made God? So that's another regress. And why then? Why would anyone make such a system? Well, of course, you know a number of ideas. You can make suggestions. Others include, how can we access the system behind the system? Is it possible? Maybe that's what magic is. Can we do this? I believe we can, and I believe people have. What further experiments could we do to prove this interpretation? What other evidence do we have for this interpretation? I can give quite a few, in fact, and maybe you can too. So get in touch with me, make propositions and ask questions and try and throw me over here and say this is all nonsense, and maybe it is. I can give quite a few ideas here, and I will do this in a further essay, but let's see what you have to say first. Thank you for listening.